Everything you have ever known, every person you have ever loved, and every star you have ever seen began as an impossible glitch in a void that shouldn't have existed. We are the survivors of a cosmic accident so violent and so profound that it defies the very laws of logic we use to measure it. Before the dawn of light, there was only the cold, silent hunger of non-being. If you find the mysteries of our origin as gripping as I do, please subscribe to the channel for more explorations into the deep cosmos. Now we begin our journey into the absolute beginning of time. To understand how everything we see emerged from nothing, we first have to confront a terrifying truth. Our human intuition about what is empty and what is full is fundamentally wrong. When we look at a glass of water and call it empty, we know there is still air inside. When we look at the vacuum of space between the stars and call it empty, we are still missing the point. Even if you were to strip away every single atom, every photon of light, and every stray neutrino from a cubic meter of space, what remains is not nothing. It is a stage, it is a fabric, it is a physical entity that can bend, stretch, and ripple. But to find the true origin of the universe, we have to go back further, to a state where even the stage itself did not exist. We have to talk about the true nothing, the philosophical nothing, and then we have to explain how physics makes that state impossible to maintain. The journey starts with the realization that the universe is currently expanding. If you were to hit the rewind button on the history of the cosmos, you would see the galaxies moving closer and closer together. The light from distant stars would shift from red to blue as the distance between us shrank. Eventually, all the matter and energy in the visible universe, which spans 93 billion light-years today, would be crushed into a space the size of a galaxy, then the size of a solar system, then the size of a single sun. As we keep rewinding the clock, we reach a point 13.8 billion years in the past, where everything is concentrated into a space smaller than a single atom. This is what we call the singularity. At this point, the density is infinite, and the temperature is so high that the laws of physics as we know them simply cease to function. General relativity, Albert Einstein's masterpiece that describes gravity and the shape of space, tells us that at this point, the curvature of space-time becomes infinite. But infinite is just a fancy word scientists use when the math breaks down and they don't know what happens next. This breakdown is our first clue. It suggests that space and time are not fundamental. They are emergent. They are things that can be created. To see how they were created, we have to look into the world of the incredibly small, the world of quantum mechanics. In our everyday lives, we are used to the idea that if you have $0 in your bank account, you have nothing. But in the quantum world, zero is never really zero. There is a principle called the Heisenberg uncertainty principle, and it is the most important rule in the history of existence. It tells us that there is a fundamental limit to how much we can know about a system. You cannot know both the position and the momentum of a particle with perfect precision. But more importantly for our story, the principle also applies to energy and time. It says that over a very, very short period of time, the amount of energy in a vacuum can fluctuate wildly. Imagine a perfectly flat, still ocean. To a casual observer, it looks like there is nothing happening, but if you were to zoom in with a powerful enough microscope, you would see that the surface is actually a chaotic mess of tiny bubbles and ripples appearing and disappearing in the blink of an eye. This is what the vacuum is like. It is a sea of quantum fluctuations. Particles and their antimatter counterparts are constantly popping into existence out of the void, borrowing energy from the future, and then colliding and annihilating each other almost instantly, returning that energy before the universe can notice the debt. These are called virtual particles. They aren't just a theoretical trick. We have measured their effects in laboratories. We know that the void is alive with energy. So, if the vacuum is already boiling with potential, the question becomes, how did one of those tiny microscopic fluctuations turn into a trillion tons of matter? How did a quantum hiccup become a Big Bang? The answer lies in a concept known as the zero-energy universe hypothesis. It sounds like a paradox, but it is one of the most elegant ideas in science. Think about a mountain and a hole in the ground. If you take the dirt from the hole to build the mountain, the net change in the amount of dirt is zero. You have a positive mountain and a negative hole. The universe works in a very similar way. Matter and energy are positive. They have a certain mass, and mass is energy, as Einstein showed us with his famous equation, E=mc². But gravity is negative. Because gravity is an attractive force, it takes energy to pull things apart against its grip. If you calculate the total amount of positive energy in all the matter in the universe and add it to the total amount of negative gravitational energy, the sum might be exactly zero. If this is true, then the universe didn't require any net energy to be created. It is the ultimate free lunch. But even a free lunch needs a cook. It needs a mechanism to take that initial tiny fluctuation and blow it up before it can disappear back into the void. This brings us to the epoch of cosmic inflation. This is a period of time so brief and so violent that it defies human comprehension. It happened roughly 10 to the power of negative 36 seconds after the beginning. During this sliver of a moment, the universe didn't just expand, it exploded in scale. It grew by a factor of at least 10 to the power of 26. To put that in perspective, imagine a single atom suddenly growing to the size of the entire Milky Way galaxy, and imagine it happening in a trillionth of a trillionth of a trillionth of a second. This expansion was driven by a mysterious field called the inflaton field. As this field settled into a lower energy state, it acted like a repulsive form of gravity, pushing the fabric of space apart faster than the speed of light. This is a crucial point. The speed of light is the speed limit for objects moving through space, but there is no speed limit for space itself. Space can expand as fast as it wants. During inflation, the universe was smoothed out. Any wrinkles or irregularities were stretched so thin that they disappeared, which explains why the universe looks the same in every direction we look today. But as the inflation period came to an end, the energy stored in that inflaton field had to go somewhere. It decayed. It dumped its vast reserves of energy into the vacuum, and in a process called reheating, the universe was flooded with a hot, dense soup of particles. This was the moment the Big Bang actually became big. The cold, empty, inflating void was suddenly a furnace of unimaginable heat. In these first few moments, the temperature was so high that even the fundamental forces of nature were not yet distinct. We believe that at the very beginning, gravity, electromagnetism, and the strong and weak nuclear forces were all merged into one single super force. As the universe cooled, these forces began to split apart, like water freezing into ice. This process is called symmetry breaking. Each time a force split off, it released more energy, further fueling the expansion. By the time the universe was 10 to the power of negative 12 seconds old, the four forces we know today were established, and the stage was set for the creation of matter as we know it. But even then, the universe was not a place we would recognize. It was filled with a quark gluon plasma, a substance so hot that atoms couldn't form. Protons and neutrons couldn't even exist. It was just a chaotic swirl of the most basic building blocks of reality. And here we encounter one of the greatest mysteries in all of science. For every billion particles of antimatter created in the early universe, there were 1,000,001 particles of regular matter. As the universe cooled slightly, these particles met and destroyed each other, turning back into pure light. If the numbers had been perfectly equal, there would be nothing left in the universe today but radiation. There would be no stars, no planets, and no people. But for some reason, there was a tiny excess of matter. We are the leftovers of that ancient, lopsided massacre. Every atom in your body is a survivor of a war that happened when the universe was less than a second old. As the clock ticked forward to 1 second, the temperature dropped to about 10 billion degrees. Now, the quarks could finally clump together to form protons and neutrons. These are the hearts of atoms. For the next few minutes, the entire universe acted like the core of a star. It was a giant fusion reactor. Protons and neutrons collided and stuck together to form the first nuclei of light elements: hydrogen, helium, and a tiny bit of lithium. This process, called Big Bang nucleosynthesis, lasted for only about 20 minutes. After that, the universe had expanded and cooled so much that the fusion stopped. The chemical composition of the universe was essentially locked in, about 75% hydrogen and 25% helium. To this day, when we look at the oldest stars and the most distant gas clouds, we see exactly this ratio. It is one of the strongest pieces of evidence we have that this entire story is true. But even though we had nuclei, we didn't have atoms yet. The universe was still far too hot for electrons to settle into orbits around those nuclei. Instead, the electrons flew around wildly, crashing into photons of light. This made the early universe a thick, opaque fog. Light couldn't travel more than a tiny distance before being deflected. If you had been there, you wouldn't have been able to see anything, even though there was light everywhere. The universe was a glowing, white-hot wall of plasma. It stayed this way for a long time. Not seconds or minutes, but hundreds of thousands of years. As the universe continued to stretch, the wavelength of the light within it stretched as well, losing energy and cooling down. Finally, 380,000 years after the beginning, the temperature dropped to about 3,000 degrees Kelvin. This was the threshold. The electrons finally slowed down enough to be captured by the hydrogen and helium nuclei. This event is known as recombination. Suddenly, the fog cleared. The photons, no longer harassed by free electrons, were free to fly across the cosmos in straight lines. For the first time in history, the universe became transparent. The light from that moment is still traveling through space today. Because of the expansion of the universe, that light has been stretched so much that it is no longer visible to the human eye. It has shifted all the way down into the microwave part of the spectrum. We call it the cosmic microwave background radiation. It is a faint hiss of energy that fills the entire sky, coming from every direction. It is the oldest thing we can ever see. It is a snapshot of the universe when it was an infant. When scientists first mapped this radiation with satellites like Planck and WMAP, they found something incredible. The map wasn't perfectly smooth. There were tiny microscopic variations in temperature, differences of only 1/100,000th of a degree. These tiny ripples are the most important structures in history. They are the imprints of those original quantum fluctuations from the very beginning, stretched out to cosmic scales by inflation. These slightly denser regions had a little bit more gravity than the areas around them. Over the next few 100 million years, that gravity would act like a magnet, pulling in more and more gas. But after the initial flash of the cosmic microwave background, the universe entered a period known as the Dark Ages. There were no stars yet. There were no galaxies. There was just a vast, cold and dark sea of hydrogen and helium gas, slowly clumping together under the relentless pull of gravity. This period lasted for about 100 million to 200 million years. It was a time of profound silence and darkness. But beneath that darkness, something was brewing. The dense pockets of gas were getting hotter and tighter. The pressure at the center of these clouds was reaching a breaking point. Eventually, in the heart of one of these clouds, the temperature hit 10 million degrees. Gravity finally won its battle against pressure, and the first star ignited. This was the cosmic dawn. The first light since the Big Bang began to flood the universe. These first stars were nothing like the sun. They were giants, hundreds of times more massive than our star, and they burned with a fierce blue-white intensity. They lived fast and died young. But in their deaths they did something miraculous. The Big Bang had only created light elements like hydrogen and helium. It didn't create the carbon in your DNA, the oxygen you breathe, or the iron in your blood. Those elements can only be forged in the intense heat and pressure of a dying star. When those first stars exploded as supernovae, they scattered these new heavy elements into space, seeding the clouds of gas that would become the next generation of stars and planets. This cycle of birth and death continued for billions of years, building the complex structures we see today. Gravity continued to pull together groups of stars into the first small galaxies, and those galaxies collided and merged to form the massive spirals and ellipticals that populate our sky. About 9 billion years after the Big Bang, in a quiet corner of a nondescript spiral galaxy, a new star began to form from a cloud of gas enriched by the dust of countless previous generations of stars. This was our Sun, and around it, the leftover debris began to clump together to form the Earth. When we look back at this entire chain of events, it is easy to feel small. We are living on a tiny rock orbiting a middle-aged star in a universe that is so vast, it makes our entire history look like a blink of an eye. But there is another way to look at it. We are the way that the universe knows itself. The atoms in your left hand probably came from a different star than the atoms in your right hand. You are literally made of stardust that has been recycled over billions of years, and all of that stardust can be traced back to a single tiny quantum fluctuation in a void of nothingness. The story of the universe is not just a story of physics and math. It is our story. It is the story of how nothing became everything, and how that everything eventually became conscious enough to ask where it came from. We are still uncovering the details. We still don't know what dark matter is, or what dark energy is doing to the future of our cosmos. We don't know if our universe is the only one, or if it is just one bubble in a vast multiverse of infinite possibilities. But the fact that we can even ask these questions is a testament to the incredible journey we have taken. Think about the sheer scale of time we are discussing. If the entire history of the universe were compressed into a single calendar year, with the Big Bang happening at the very first second of January 1st, then the first stars wouldn't appear until late January. Our galaxy, the Milky Way, would form in March. But our own solar system wouldn't even exist until late August. The first life on Earth would appear in September, and dinosaurs wouldn't roam the planet until December 26th. Entire human history, from the first stone tools to the device you are using to listen to this, would occupy only the last few seconds of December 31st. We are brand new here, and yet we have managed to look back and decode the light of the beginning. The more we learn about the origin of the universe, the more we realize that the boundary between nothing and something is incredibly thin. Physics suggests that the universe might have a total energy of zero, meaning it is essentially a very complex rearrangement of nothingness. This doesn't make it any less real. In fact, it makes it more beautiful. It means that existence is not a burden on the void, but a possibility within it. The vacuum wasn't empty, it was pregnant with everything we see. As we look deeper into the cosmos with our telescopes, we are literally looking back in time. We see galaxies as they were billions of years ago because their light has taken that long to reach us. We are looking at the ghosts of the past to understand our future. And what that past tells us is that change is the only constant. From the first frantic seconds of inflation to the slow, steady burn of the stars today, the universe has never stopped evolving. It is a dynamic, living system. But what happens next? If the universe started from a fluctuation in the vacuum, does it have to end? Current observations show that the expansion of the universe is not slowing down, it is accelerating. A mysterious force called dark energy is pushing the galaxies apart faster and faster. If this continues, in trillions of years, every galaxy will be so far apart that they will be invisible to each other. The stars will eventually run out of fuel and go dark. The universe will become a cold, empty void once again. It seems that we are living in a brief golden age of light and complexity, sandwiched between two eternities of darkness. But even in that distant, dark future, the laws of quantum mechanics will still apply. The vacuum will still be boiling with potential. Virtual particles will still be popping in and out of existence. Perhaps in some unimaginably distant era, another fluctuation will happen. Another inflaton field will trigger another burst of expansion. Another Big Bang will create another universe, with its own laws of physics and its own story to tell. The cycle of nothing becoming something might be an infinite one. We often think of the universe as a place that we are in, like a fish is in the ocean. Но это не совсем так. We are the universe. We are part of its fabric. The carbon, nitrogen, and oxygen atoms in our bodies were created in the hearts of stars. The hydrogen that makes up the water in our cells was created in the first few minutes of the Big Bang. When you look at the stars, you aren't looking at something far away and disconnected. You're looking at your ancestors. You're looking at the oven that baked the ingredients for your life. This realization brings a sense of cosmic perspective. The petty squabbles and daily stresses of our lives seem much smaller when viewed against the backdrop of 13.8 billion years of history. We are a way for the cosmos to see itself, to hear itself, and to wonder about itself. Every time we point a telescope at the sky or build a particle accelerator to smash atoms together, we are the universe trying to understand its own origin. We are the curiosity of the void made manifest. The transition from the hot, dense state of the early universe to the cold, structured universe of today was a series of narrow escapes. If the strong nuclear force had been just a few % weaker, protons couldn't have stuck together, and the only element in the universe would be hydrogen. If gravity had been slightly stronger, the universe would have collapsed back on itself long ago in a big crunch. We live in a universe that seems almost tuned for the existence of complexity. Whether this is due to chance or whether it is because we live in a multiverse where every possible version of a universe exists, and we just happen to be in one where life is possible, is one of the most profound questions in modern science. The story of how we got here is still being written. Every year we find new planets around distant stars, some of which might have liquid water and the potential for life. Every year we refine our measurements of the cosmic microwave background, looking for even deeper clues about the first trillionth of a second. We are living in a golden age of astronomy. We have the technology to see the beginning of time and the intellectual tools to understand what we are seeing. But even as we find more answers, the mystery of nothing remains. Why is there something rather than nothing? Why do the laws of physics exist at all? These are questions that push the limits of science and enter the realm of philosophy. But physics gives us a starting point. It tells us that nothingness is unstable. It tells us that the void is not a state of rest, but a state of potential. The universe exists because it could not help but exist. It is the inevitable result of the laws of quantum mechanics acting on the vacuum. As we continue our journey through the stars, we carry this knowledge with us. We are the descendants of the Big Bang. We are the children of the stars, and we are the explorers of the void. The journey that started 13.8 billion years ago is still going on, and we are its current protagonists. The light that started its journey across the cosmos when the first stars ignited is finally hitting our telescopes, and in that light, we see our own reflection. Understanding the origin of the universe is not just about understanding the past. It is about understanding our place in the present. It tells us that we are part of a vast interconnected system that has been unfolding for eons. It tells us that we are made of the same materials as the most distant galaxies. And it tells us that even in a universe that seems vast and indifferent, there is a place for consciousness, for curiosity, and for wonder. The transition from a quantum fluctuation to a world of mountains, oceans, and people is the most incredible story ever told. It is a story of incredible violence and beautiful order. It is a story of darkness being conquered by light, and of simplicity giving birth to complexity. And the most amazing part of the story is that we are here to tell it. We have climbed out of the gravitational well of our planet to look back at the beginning of everything. As we look out into the night sky, we aren't just seeing points of light. We are seeing the history of the universe written in the stars. We are seeing the light of the Big Bang, stretched and cooled but still present. We are seeing the remnants of the first stars, whose deaths gave us the atoms of our bodies. We are seeing the ongoing expansion of space, the silent stretching of the fabric of reality. The silence of the void is not the silence of death, but the silence of anticipation. The nothingness that came before the Big Bang was not a void of absence, but a void of potential. It was a blank canvas waiting for the first brushstroke of energy. And once that stroke was made, the universe began an unstoppable dance of creation that is still happening today. Every time a new star is born, every time a planet forms, every time a child is born, the Big Bang continues. We are the living evidence of the universe's creativity. We are the result of billions of years of cosmic evolution. And as we continue to study the heavens, we are not just looking for facts. We are looking for meaning. We are looking for our place in the grand design. And what we find is that the design is more magnificent than we ever could have imagined. The journey from nothing to everything is a journey of endless wonder, and we are just getting started. In the vast timeline of the cosmos, our lives are incredibly brief. But our ability to understand the universe gives us a kind of immortality. By uncovering the secrets of the Big Bang, we connect ourselves to the very beginning of time. We become part of the grand story that spans billions of years and trillions of miles. We are no longer just inhabitants of a small planet. We are citizens of the cosmos. The exploration of our origins is the ultimate human endeavor. It is what separates us from every other species on Earth. We are the only ones who look at the stars and ask why they are there. We are the only ones who try to build a mathematical model of the beginning of time. This drive to know, to understand, and to explore is what makes us human, and it is what will eventually lead us to the next great discovery, whatever that may be. As we conclude this part of our journey, we must remember that the universe is under no obligation to make sense to us, and yet it does. The fact that the human mind, which evolved to find food and avoid predators on the African savanna, can understand the quantum mechanics of the early universe is perhaps the greatest miracle of all. It suggests a deep connection between the laws of the cosmos and the laws of thought. It suggests that we are exactly where we are supposed to be. The story of the universe is still unfolding, and there are many chapters yet to be written. We are the ones holding the pen. With every new discovery, we add a new line to the story. With every new telescope we launch, we see a little bit further into the past. The journey from nothing to everything is the greatest adventure in history, and we are privileged to be a part of it. The light of the first stars is still out there, traveling through the darkness. The echoes of the Big Bang are still ringing through the fabric of space, and the curiosity that drives us to understand it all is still burning bright. We are the universe's way of looking at itself, and what we see is beautiful. We see a cosmos that is vast, complex, and full of potential. A cosmos that started from nothing and became everything. And a cosmos that is still full of mysteries waiting to be solved. The atoms in your body have been on a journey of 13.8 billion years to get to where they are today. They have been inside the hearts of stars, they have been ejected into the cold vacuum of space, they have been part of ancient nebulae, and they have been recycled through generations of living things. You are a temporary vessel for these ancient travelers, and one day those atoms will continue their journey, returning to the Earth and eventually to the stars. This cycle of matter and energy is the fundamental rhythm of the universe. It is a rhythm that started with a single silent beat in the void. From that one beat, all the complexity of the world has emerged. The music of the spheres is not a metaphor, it is a description of the vibrating fields that make up our reality. And we are the ones who have learned to hear the music. As we look forward to the future of our exploration, we should feel a sense of pride. We have come so far in such a short amount of time. From huddling in caves to mapping the cosmic microwave background, our progress has been extraordinary. But we must also feel a sense of humility. The universe is much larger and much older than we can truly grasp. We are just a small part of a much bigger story. The journey from nothing to everything is not just a scientific theory, it is a testament to the power of possibility. It tells us that even in the most absolute darkness, there is the potential for light. It tells us that even in the most empty void, there is the potential for life. And it tells us that no matter how small we may feel, we are part of something truly grand. The story of the universe is our story. It is the story of our origins, our evolution, and our destiny. And it is a story that is still being told. Every night when the sun goes down and the stars come out, we are reminded of where we came from. We are reminded of the long, strange journey that brought us here, and we are reminded that the universe is still full of wonders, waiting for us to find them. The transition from the singularity to the present day is a bridge across time and space. It is a bridge built of light, gravity, and quantum mechanics, and we are the ones walking across that bridge, looking back at the beginning and forward to the future. The journey is long and the path is not always clear, but the destination is nothing less than the truth about our existence. The more we study the beginning of the universe, the more we realize that the universe is not just a collection of objects, but a process. It is something that is happening. It is an ongoing event. The Big Bang didn't just happen once. Its energy is still driving the expansion of the cosmos. Its heat is still radiating through space. Its laws are still governing the behavior of every atom and every galaxy. We are part of that ongoing event. The realization that we are made of stardust is one of the most profound insights in history. It connects us to the cosmos in a way that is both scientific and spiritual. It tells us that we are not strangers in a strange land, but are at home in the universe. We are made of the same stuff as the stars, and we are governed by the same laws. We are part of the cosmic family. As we continue to explore the mysteries of the universe, we must stay curious. We must keep asking the big questions. We must keep looking for the truth, no matter where it leads us. The journey from nothing to everything is a journey that has no end. There will always be more to learn, more to discover, and more to wonder about. And that is what makes it so exciting. The story of how the universe began is a story of hope. It tells us that even from nothing, something magnificent can grow. It tells us that the universe is a place of endless possibility, and it tells us that we are part of that possibility. We are the ones who can see the beauty of the cosmos, who can understand its laws, and who can marvel at its scale. We are the universe's crowning achievement. The light of the beginning is still shining, the energy of the Big Bang is still flowing, and the story of the universe is still being written. We are the ones who get to read it, and we are the ones who get to write the next chapter. The journey from nothing to everything is the greatest story ever told, and we are lucky to be a part of it. Let us continue to look up at the stars and wonder. Let us continue to explore the mysteries of the void. And let us never forget that we are made of the same stuff as the stars. The universe started with a spark, a tiny flicker of energy in a silent void. That spark became a flame, and that flame became a furnace, and that furnace became the world we see today. It is a journey of 13.8 billion years, and it is a journey that is still going on. We are the current witnesses to this incredible process. We are the ones who have the privilege of looking back and seeing how it all began. As we peer into the depths of space, we are looking into our own past. We are looking at the origins of our atoms and the birth of our world. We are looking at the long, slow process of cosmic evolution that has led to us. And what we see is a universe that is full of beauty, complexity, and mystery. A universe that is constantly changing and constantly growing. The story of the universe is a story of transition. from the infinite density of the singularity to the vast emptiness of the modern cosmos, from the hot, dense plasma of the early universe to the cold, structured galaxies of today, from the simple elements of hydrogen and helium to the complex chemistry of life. It is a story of endless change and endless progress. The realization that the universe emerged from nothing is perhaps the most challenging and exciting idea in all of science. It forces us to rethink our ideas about reality and existence. It tells us that the world is much more mysterious and much more wonderful than we ever imagined, and it gives us a new perspective on our own lives and our own place in the cosmos. As we continue to explore the universe, we must remember that we are just at the beginning of our journey. We have so much more to learn and so much more to discover. The universe is full of secrets, and we are just starting to uncover them. But with every new discovery, we come a little bit closer to understanding the true nature of our existence. The journey from nothing to everything is a journey of discovery, of wonder, and of awe. It is a journey that takes us from the smallest particles to the largest galaxies. It is a journey that takes us from the beginning of time to the present day, and it is a journey that we are all taking together. Let us continue to explore, to learn, and to wonder. The universe is waiting for us. To truly grasp the magnitude of how nothing became everything, we have to look even closer at that first trillionth of a second, a period of time so short that the word second loses all meaning. This is the Planck epoch, a realm where space and time as we understand them simply dissolve. In this state, the universe was smaller than the smallest subatomic particle, yet it contained the potential for every galaxy that would ever exist. Scientists believe that at this density, the geometry of space-time itself was fluctuating wildly, a state known as quantum foam. Imagine the very fabric of reality being torn and restitched millions of times every moment. There was no left or right, no up or down, and arguably no before or after. It was a state of pure, unadulterated potential. This is the ultimate starting point, the moment where the rules of the game were being written. As the universe began its initial expansion, it went through a series of phase transitions. Think of it like steam cooling down to become liquid water and then freezing to become ice. Each of these transitions changed the very nature of reality. The first major transition was the separation of gravity from the other three fundamental forces. Before this, physics was unified. There was one single law governing everything. But as the universe cooled slightly, gravity broke away, becoming the master of the large-scale structure of the cosmos. This was followed by the separation of the strong nuclear force, which is the glue that holds atoms together. This separation was so energetic that it likely triggered the era of cosmic inflation we discussed earlier. It was a massive discharge of energy, like a cosmic lightning bolt, that stretched the universe from the size of a marble to the size of a solar system in an instant. But what drove this expansion? We often talk about the Big Bang as a push, but it might be better to think of it as a fall. Physicists propose the existence of a scalar field called the inflaton field. In its high-energy state, this field caused space to expand exponentially. But this state was unstable. Like a ball perched precariously at the top of a hill, the field eventually rolled down to a lower energy state. As it fell, it released its stored energy into the vacuum. This energy didn't just disappear, it transformed. Through the famous principle of mass-energy equivalence, that raw energy condensed into the first particles of matter. It was the ultimate conversion of potential into reality. However, this creation of matter was fraught with danger. In the early high-energy environment, matter and antimatter were being created in equal amounts. Antimatter is the perfect mirror image of matter, but with an opposite charge. When they meet, they annihilate each other in a flash of pure energy. In those first moments, the universe was a chaotic battlefield of annihilation. For every billion particles of matter and antimatter that destroyed each other, only one single particle of matter survived. This tiny asymmetrical residue is what makes up everything we see today. If the universe had been perfectly symmetrical, if the laws of physics had treated matter and antimatter with absolute equality, there would be nothing but light today. No stars, no planets, and no one to wonder why. This slight imperfection, this 1 in a billion mistake, is the reason we exist. As the universe continued to cool, the next major milestone was the electroweak transition. This is when the electromagnetic force and the weak nuclear force, which were previously one and the same, split into the distinct forces we measure today. This was the moment that particles like electrons and neutrinos gained their masses. Before this, they were zipping around at the speed of light, massless and ethereal. but through their interaction with the Higgs field, a field that permeates all of space, they began to feel a kind of cosmic drag. This drag is what we perceive as mass. It gave the universe substance. It allowed particles to slow down enough to eventually form structures. Without the Higgs field, the universe would be a frantic, light-speed blur of energy that could never clump together to form anything interesting. By the time the universe was 1 microsecond old, it was a boiling sea of quarks and gluons. Quarks are the fundamental building blocks of protons and neutrons, but at this stage the temperature was too high for them to bind together. They existed as a quark-gluon plasma, a substance that behaves more like a perfect liquid than a gas. Scientists have actually recreated this state of matter in the Large Hadron Collider, giving us a fleeting glimpse into the conditions of the universe just moments after its birth. As the temperature dropped further, the strong force finally took hold, chaining the quarks together in groups of 3 to form protons and neutrons. This was a point of no return. The building blocks of the chemical elements were now firmly established. For the next few minutes, the entire universe was a nuclear furnace. This is the era of nucleosynthesis. The density was still high enough that protons and neutrons were constantly colliding and fusing, but this window of opportunity was short. Because the universe was expanding so rapidly, the density and temperature were dropping fast. By the time the universe was 20 minutes old, it was too thin for further fusion to occur. This is why the early universe only produced the lightest elements. It was a race against time, and the expansion of space eventually won. The cosmos was left with a vast majority of hydrogen, about 25% helium, and a trace amount of lithium. Every other element, from the carbon in your cells to the gold in your jewelry, had to wait billions of years to be forged in the hearts of stars. We are, in a very real sense, the latecomers to the cosmic party. After this frantic burst of activity, the universe settled into a long period of quiet cooling. This was the era of the plasma fog. For 380,000 years, the universe was an opaque, glowing soup. Light could not travel through it. Photons were constantly bouncing off free electrons, like a silver ball in a cosmic pinball machine. If you could have stood in the universe during this time, it would have looked like being inside a thick, orange-white fog. There were no stars, no shadows, just a uniform, blinding glow. This era only ended when the universe cooled enough for electrons to be captured by nuclei, creating neutral atoms. This was the moment of recombination, and it changed the universe forever. When the electrons were captured, the photons were suddenly set free. They could finally travel across the universe in straight lines. This was the first light, the oldest signal we can ever receive. Today we see this light as the cosmic microwave background radiation. When we point our microwave telescopes at the sky, we are looking at the afterglow of the Big Bang itself. But this light also reveals something hidden. It shows us that the early universe was not perfectly smooth. There were tiny microscopic ripples in the density of the gas. These ripples were the seeds of everything. Without these tiny fluctuations, which originated as quantum vibrations during inflation, gravity would have had nothing to pull on. The gas would have stayed perfectly uniform, and the universe would have remained a featureless, expanding cloud of hydrogen. Instead, the regions that were slightly denser than their surroundings began to act as gravitational traps. Over the next few 100 million years, these traps pulled in more and more gas. This was the beginning of the Dark Ages. The universe was expanding, cooling, and dark. But inside these growing clouds of gas, something incredible was happening. The gas was being compressed. As it compressed, it heated up. This was a battle between the outward pressure of heat and the inward pull of gravity. Eventually, in the centers of the most massive clouds, gravity won. The temperature reached the point of nuclear ignition, and the first stars flickered into life. This was the end of the Dark Ages and the beginning of the cosmic dawn. These first stars, known as population 3 stars, were very different from our Sun. Because the universe was still mostly hydrogen and helium, these stars could grow to be enormous, sometimes hundreds of times more massive than the Sun. They were incredibly hot and incredibly bright, burning through their fuel in just a few million years. Their intense ultraviolet light stripped the electrons back off the surrounding hydrogen gas, a process called rionization. This made the universe transparent to even more types of light, allowing us to see further back into history. But the most important contribution of these first stars was their death. When they ran out of fuel, they exploded in colossal supernovae, scattering the first heavy elements, carbon, oxygen, silicon, into the void. This was the first time the universe had the ingredients for planets and life. As these first stars died, their remnants often collapsed into black holes. These black holes acted as anchors, drawing in even more gas and other stars to form the first proto-galaxies. Over billions of years, these small galaxies collided and merged, growing into the majestic structures we see today. In the centers of these galaxies, supermassive black holes formed, millions or even billions of times more massive than the Sun. These monsters regulated the growth of their host galaxies, blowing out gas with powerful jets and preventing too many stars from forming at once. The history of the universe is a history of this delicate balance between the creative power of gravity and the destructive power of radiation. While all of this was happening with visible matter, there was a silent partner in the room: dark matter. We still don't know what dark matter is, but we know it's there because we can see its gravitational influence. It doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. But it makes up about 85% of the matter in the universe. In the early universe, dark matter formed a vast, invisible web, a cosmic scaffolding. The regular matter, the gas that would become stars, simply fell into the gravitational wells created by this dark matter. Without dark matter, there wouldn't have been enough gravity to pull the first galaxies together in time. We owe our existence to a ghost-like substance that we still cannot explain. And then, about 5 billion years ago, another mysterious force began to dominate the cosmos. For most of the universe's history, gravity was the primary player, slowing down the expansion that started with the Big Bang. But as the universe grew larger and galaxies moved further apart, gravity's grip began to weaken. This allowed dark energy, a mysterious pressure that seems to be a property of space itself, to take over. Dark energy doesn't clump like matter, it is uniform and repulsive. It acts like an anti-gravity, pushing the fabric of space apart at an accelerating rate. We discovered this only recently, in the late 1990s, and it completely changed our understanding of the universe's fate. Instead of slowing down or collapsing back, the universe is flying apart faster and faster every second. This means that we are living in a very special time in cosmic history. Right now, the galaxies are close enough together that we can see them. The cosmic microwave background is still detectable, but in the far future, dark energy will have pushed the other galaxies so far away that their light will never reach us. The universe will become a lonely place. Future astronomers on a planet orbiting a distant star might look at the sky and see nothing but the stars in their own galaxy. They might never know that other galaxies exist, or that there was once a Big Bang. The evidence of our origin is slowly being erased by the expansion of space. We are the first generation of humans to understand the beginning, and we might be among the last to have all the evidence available to us. Think about the sheer complexity that has emerged from that initial nothingness. From a single quantum fluctuation, we have evolved a universe with hundreds of billions of galaxies, each containing hundreds of billions of stars. We have planets with complex atmospheres, oceans, and life. And on at least one of those planets, life has evolved to the point where it can build machines to look back at the beginning of time. This is the ultimate triumph of the universe. It is not just a collection of dead matter, it is a system that can produce intelligence and awareness. When we study astronomy, we are not just looking at cold, distant objects. We are looking at our own roots. We are looking at the laboratory where our atoms were created and the stage where our history was written. The mystery of why there is something rather than nothing remains the ultimate question. Some physicists suggest that the universe didn't just happen once, but is part of a much larger structure called the multiverse. In this view, our Big Bang was just one of many, a single bubble in a vast eternal sea of inflation. Each bubble might have different laws of physics, different numbers of dimensions, and different constants. We find ourselves in this particular universe because it is one of the few where the conditions are just right for life to emerge. This is known as the anthropic principle. It suggests that our existence is not a miracle, but a statistical inevitability in a sufficiently large multiverse. Others suggest that the universe might be a hologram, a two-dimensional surface that projects a three-dimensional reality. In this theory, all the information about our three-dimensional world is stored on the boundary of the universe, much like the data on a credit card chip. This sounds like science fiction, but it is a serious mathematical possibility that arises from the study of black holes and quantum gravity. It suggests that our common sense ideas about space and time are just approximations, and that the true nature of reality is something much more abstract and data-driven. But regardless of which theory is correct, the story of the universe is a story of incredible resilience. It has survived the intense heat of the first few minutes, the long darkness of the Dark Ages, and the violent collisions of galaxies. It has transformed from a state of zero entropy and infinite potential into a vast, complex, and beautiful tapestry. And it has done all of this while seemingly obeying a simple set of mathematical laws. The fact that the universe is even understandable to us is perhaps the most surprising thing of all. As Albert Einstein once said, the most incomprehensible thing about the world is that it is at all comprehensible. As we look at the stars tonight, we should remember that we are part of this grand narrative. Every photon of light that hits your eye has its own story to tell. Some have been traveling for millions of years from distant galaxies. Others were created just a few minutes ago in the heart of the sun. But all of them can be traced back to that same initial point of origin. We are all connected by the same history and the same laws of physics. We are all citizens of a universe that came from nothing and became everything. The transition from the early, hot universe to the one we inhabit today was not a smooth one. It was a series of chaotic and violent events. There were massive bursts of radiation, the birth and death of giant stars, and the merging of entire galaxies. But out of this chaos, order emerged. The laws of gravity and electromagnetism allowed matter to organize itself into stars, planets, and eventually the complex molecules of life. This is the great paradox of the cosmos, that a system governed by the laws of entropy and decay can still produce such incredible beauty and complexity. We are currently in the stelliferous era, the age of stars. This is the period of the universe's life when the sky is full of light and galaxies are vibrant with new star formation. But this era will not last forever. In about 100 trillion years, the last stars will run out of fuel and go dark. The universe will enter the degenerate era, where the only objects left are the remnants of stars, white dwarfs, neutron stars, and black holes. Even these will eventually decay or be swallowed by black holes. Then, in the unimaginably distant future, even black holes will evaporate through a process called Hawking radiation. The universe will become a vast cold wasteland of lonely photons and electrons, spread so thin that they will never meet. But even this eventual heat death does not diminish the majesty of what is happening now. The fact that the universe has a beginning and an end gives our time in it more meaning, not less. We are living in the prime of the universe's life. We are here when the stars are bright, when the galaxies are close, and when the secrets of the cosmos are still within our reach. Our curiosity is a gift, a way for the universe to witness its own splendor before the lights eventually go out. Understanding how we came from nothing gives us a sense of perspective that is hard to find anywhere else. It reminds us that our differences are tiny compared to the vast scales of space and time. It reminds us that we are all made of the same stardust and that we all share the same cosmic heritage. In a world that often feels divided and chaotic, the story of the universe offers a sense of unity and purpose. We are the explorers of the void, the decoders of the light, and the storytellers of the beginning. The journey from the quantum vacuum to the modern world is a journey of increasing complexity and awareness. It is a journey that has taken 13.8 billion years, and it is a journey that is still ongoing. We are the latest chapter in that story, but we are not the last. What the future holds for our species and our universe is still unknown. But as long as we keep looking up and asking questions, we are honoring the incredible process that brought us into being. Every time we discover a new planet, every time we detect a gravitational wave from a distant collision, every time we refine our understanding of the early universe, we are adding another page to the book of everything. We are slowly but surely mapping the territory of our origin, and what we find is always more surprising and more beautiful than we expected. The universe is not just a place where things happen, it is a masterpiece of physics and chance, a grand experiment that has been running since the dawn of time. The concept of a universe from nothing is perhaps the most profound realization in the history of human thought. It bridges the gap between science and philosophy, between the physical and the metaphysical. It tells us that existence is a miracle of physics, a spontaneous eruption of energy and matter that has led to the incredible world we see around us. It is a story that begins with a silent void and ends with a conscious mind. And it is a story that we are all lucky enough to be a part of. The more we look into the past, the more we see the interconnectedness of all things. The calcium in your bones was forged in the same type of explosion that created the dust clouds of distant nebulae. The iron in your blood is a direct result of the death of a massive star billions of years ago. We are literally connected to the rest of the universe by a web of physical history. To know the stars is to know ourselves. As we move forward, we must continue to support the curiosity and the science that allow us to tell this story. We must continue to build the telescopes, the particle accelerators, and the mathematical models that peel back the layers of reality. Because in doing so, we are not just satisfying our curiosity, we are fulfilling our role as the eyes and ears of the cosmos. We are the ones who can appreciate the grand design, who can see the beauty in the numbers, and who can feel the awe of the infinite. The story of how nothing became everything is the ultimate epic. It has a dramatic beginning, a complex middle, and a mysterious end. It has heroes in the form of stars and galaxies, and it has villains in the form of entropy and dark energy. But most of all, it has a sense of wonder that never fades. No matter how much we learn, there will always be more to discover. There will always be another mystery waiting in the dark, and that is perhaps the greatest gift of all. As we reflect on this journey, let us take a moment to appreciate the sheer improbability of our existence. We are the result of a chain of events that had to go perfectly right for 13.8 billion years. A slightly different rate of expansion, a slightly different strength of gravity, or a slightly different balance of matter and antimatter, and we wouldn't be here. We are the winners of the ultimate cosmic lottery, and we have the responsibility to use our awareness to explore, to understand, and to protect the incredible world we inhabit. The universe is a vast and ancient place, but it is also our home. It is where we came from, and it is where we belong. By understanding our origins, we find our place in the grand scheme of things. We find that we are not just small and insignificant, but are part of a process that is as old as time itself. We are the descendants of the Big Bang, the children of the stars, and the witnesses to the glory of the cosmos. And as we continue to journey through the stars, we carry the light of that beginning with us, a flame of curiosity that will never be extinguished.